You're listening to the Good Question Podcast with Richard Jacobs. Our goal is to make each of our guests exclaim, that's a good question. I don't know the answer. Because when that happens, it means you, the listener, may be inspired to learn more beyond the interview and to ask great questions yourself that lead to new insights. In this podcast, we cover historical and current anthropology, comparative religion, and history. Welcome, and let's get started.
Hello, this is Richard Jacobs with the Good Question Podcast. My guest today is Gerald Dickens. He's a professor of geology and mineralogy at Trinity College in Dublin. So we're going to talk about climate, chemistry, and life across the Paleocene-Ecocene boundary, which I understand what that means a little bit, but not fully. We'll get into it. But regardless, welcome, Gerald. Thanks for coming.
Thank you, Richard. Good to hear from you.
Yeah, tell me a bit about your background first. How did you get into studying, geology and climate, things like that?
Well, to be honest, I'm not even a geologist, which is sort of funny because I'm an endowed chair in geology. But I started out as a chemist at the University of California, and then when I graduated, I didn't want to be doing work in a chem lab for like some pharmaceutical company or something. So I actually took a few years off and worked actually as a card dealer in Nevada. And then I thought, well, that's not it's not really what I wanted to do for long term. Yeah. So then I ended up at the University of Michigan and did oceanography. And then, I was fortunate enough there, a really good program, and, met some, great colleagues who are now, good friends as a graduate student, and had some really nice mentors, and then gotten the whole idea of looking at oceans, and particularly past oceans, to understand how Earth works in the time domain. Yeah.
How do you study past oceans? Is it fossils only, or how do you even know where they were and what they were like?
Yeah. So, the main way that we do it as a community, well, think about the modern seafloor as time zero, right? So because material's landing on the seafloor. And so as you start going down from the surface into the below the seafloor, you're getting older. And so what we can do is we can understand a lot about relatively recent times by, just going out there and collecting short cores, and we can, get all sorts of information, for instance, in many locations, sort of the last 100,000 years or so. And that's just going down, in many cases, you can hit that within 10 meters. In some places, you have to go much deeper. But then if we want to understand really older sequences, then what we have to do, usually in the ocean, the modern ocean, we'd have to go out on a drill ship and then drill down, in some cases, hundreds of meters, in cases longer than a kilometer. But we also have the advantage that some of these sequences, through tectonics, and so that old pieces of the seafloor can be lifted up, and so they're exposed in land. And so we have many, many examples of this around the world. And so once you know where you are in the time domain, you can study the sort of climate change in the past, not only by looking at sediment, in the modern ocean, but also that's on land.
How deep have you observed that, pieces of the, has the mantle even poked through, X number of feet down where it's reachable, whereas it's just parts of the crust up thrust in the ocean floor?
So most places in the ocean, right? So you don't really have the mantle, but you have crust, oceanic crust, but on top of that would be sediment. But in lots of other places, we have continental crust that also has sediment on top. And so you think of it as sort of, I guess in a really simple way, think of it as sort of a cake, and the cake would be, the hard rock, and then the icing is the sediment on top. And so in many cases, we're going through this sort of, icing analog, and then going back and taking and figuring out how old something is. And there's a whole bunch of methods to do that. And then once we know the age, then we can do a whole range of, studies, everything from, as you mentioned, fossils. Many cases in the ocean, we're looking at microfossils, so things that are sort of sand-sized and smaller, but they give us lots of information. But then we can also measure, changes in other materials. So the difference in, let's say, calcium carbonate versus clay minerals. We can go in and look at the shells and do chemistry on the shells, all sorts of really fancy techniques everything from looking at complex organic molecules and how their bonds change so you give you an example of that. There's certain organic compounds that are made in the surface waters by life, and they they'll put, for example, where and how many double bonds or pentane rings are in these compounds is directly proportional to temperature. And then so what you can do is generate records, for example, of what the ratio of double bonds of some component is, and then you can backtrack out temperature through time. And yeah, lots of really.
What about if you have a cliff and then you go next to the cliff and you drill into the side of it, underwater one or an above water one? Would that allow you like a cheat to access, quote unquote, like deeper layers when you otherwise couldn't?
Oh, absolutely. And so so when you asked about, do you ever get the mantle and stuff? So there are little places where you have for example, a fault in the seafloor, and one side may be uplifted relative to the other. And you can get places where, mantle material, effectively a compound named peridotite, and you can drill into that. And so you can get a sort of a special little window if you wanted peridotite. Now, of course, the peridotite doesn't tell you too much about climate change, but tells you a lot about, all sorts of information about how, for example, Earth, works as in the tectonic sense, how plates move across their surface.
So what's some of the, the really interesting stuff that you've discovered by doing these, these drillings?
Yeah. So the one that I put, and for the highlight, the talk is something I truly find fascinating. And it's an event, and it's called the Paleocene-Eocene Thermal Maximum, or PETM. And this event, we first sort of got inklings about this happened back in about 1989, 1990. And I was just lucky that I was starting graduate school at that time. And so what it is it's an interval now. At the time, we didn't really know anything about it. But then quickly, within about 10 years, we'd figured out that this is sort of our best past analog for what our future is going to look like. And so it's a time interval, and it turns out it's about 55.9 million years ago, which seems a long time. And it's this really rapid event where temperatures across Earth's surface increase by, on average, somewhere around 6 degrees centigrade, or 10 degrees Fahrenheit, all the way from high latitudes near the poles all the way to the equator. And so you can imagine, we're as a society today, we talk about changes of one degree, 2 degrees, and then in the future, several more degrees. But we having this really rapid event in the past.
How could that have happened? How could the whole Earth have warmed like that?
Yeah, well, so there's the $64 million question. What we do know is...
Was it the $55.9 million question?
Yeah, that's a better way to put it. So we do know two fascinating things. So the first is that it's associated with a massive input of carbon, which ultimately has to be carbon dioxide. So it could be, for example, direct carbon dioxide, or it could be methane that's been converted to carbon dioxide. We can test that through lots of different ways. For example, if you add CO2, so it's happening today as we're adding a bunch of CO2 to the atmosphere, some of that CO2 is going into the ocean, and it's changing the pH of the ocean. So the pH of the ocean is dropping. So it's by several point units so far already. And so what happens when you start dropping the pH, you start dissolving up certain minerals, for example, calcium carbonate.
Yeah, certain animals can't make their shells or anything like that, right?
Yeah, and so we see all of that at the PETM. And not only that, we see what's called a carbon isotope anomaly. So we can look at, so carbon has two stable isotopes, carbon-12 and carbon-13. And the ratio of those two carbon isotopes, it varies in materials across our surface. Plants, the atmosphere, pre-industrial, has a value of something about -7 or so. And the ocean had a value of about 0. But as we're starting to pump in a lot of, CO2 coming off oil, gas, and coal, that's adding carbon that's got not only is the CO2 going up, but the carbon ratio of 13 to 12 is dropping very quickly. And because those fuels, those fossil fuels that we're burning have gone through in the ancient history, photosynthesis, which fractionates and changes the ratios. So right now we're generating this carbon isotope anomaly.
How could you generate these isotopes? I don't understand.
Okay, so if you just think, so you have two, carbon has two stable isotopes. So both of them have 6 protons. So you look on the periodic table and you see a 6, for carbon. But you have one isotope, about 99% is carbon-12, and one isotope is carbon-13, which has 7 neutrons, whereas carbon-12 has 6 neutrons. So there's a mass difference between, and that's why, like you look on the periodic table and you see, oh, it's not 12 atomic mass, it's 12.01 because you got 1% of carbon-13 atoms.
I mean, there's no process that I know of, unless nuclear, I guess, that would create
Yeah, so that
carbon-13 atoms.
exactly. So these are what we call stable isotopes. And so, when you have an isotope there, so you've heard of carbon-14. So carbon-14 is radioactive. And so what happens is you can take a nitrogen-14, you hit it with a cosmic ray, and then that goes to carbon-14, which then decays through time by a process called beta decay over about 5,700 years. And so that's when you think of, like there's radioactive isotopes, but you also have stable isotopes. And these are things that if they're in a closed box, the ratio doesn't change, except what happens is, let's say you have 2 boxes. In a really simple case, you have an atmosphere and a plant. And the plant is taking in CO2 through photosynthesis, right? But it's easier to take in a 12 carbon atom because it's got a different mass in the CO2 than a 13 carbon. So plants preferentially take in the 12 carbon. So all organic carbon, produced by plants is enriched in 12 carbon relative to some standard, which, we define as a carbonate value. And so all plants are significantly enriched in carbon-12 relative to carbon-13 relative to the atmosphere and the ocean. And then so if we take those plants and, we turn them into coal and then burn that coal, we return that carbon-12 into the atmosphere. And so what happens is the ratio of the atmosphere starts changing. And so that's...
How would this affect your ability to date things using carbon dating, the organic matter? How do you account for this change, for this preferential uptake?
That's actually a great question. So if we look at so old objects, if we go back to, let's say, the Paleoceanese, there's no carbon-14 because we're way, way past the half-life. So all carbon-14 would have decayed. So once you get beyond about 40,000 years, you can't use carbon. And so when you're looking at a million-year, but, it's important because, yeah, of course, when, let's say you have plants and you have some amount of carbon-14 in the atmosphere and carbon-13 and carbon. So now you have 3 isotopes. And if you're going to date something by radiocarbon, you have to think about how much plants are going to, and they preferentially take in 12 carbon relative to 13 carbon and definitely exclude 14 carbon. And so the plants have a starting value that you have to account for. Yeah, so all of that, that's been well known for a long time. Yeah, these processes that what we call fractionation, or is, you have a chemical process that separates the isotopes out.
Yeah, but even when you use carbon dating, how do you know how much preferential carbon-12 an organism will take up and thereby date it? I guess, when they die, there's no preferential uptake, but still, how do you know what the difference will be?
So what you do is so you have a plant. The plant's at time 0, and so it's pulling carbon out of the atmosphere, and it's uptaking through photosynthesis carbon-12, carbon-13, and carbon-14. Well, the ratio of carbon-12 and 13, we know the fractionation process. What we don't know when the plant is formed, and this is a really important concept, is we don't know the carbon-14 content in the atmosphere, let's say, 5,000 years ago, because it depends on the flux of cosmic rays. And so the amount of carbon-14 relative to the other 2 isotopes can vary in the time domain, as well as, any sort of fluctuations like us coming along as humans and adding preferentially carbon-12 back to the atmosphere. So the composition and the relative ratios are changing through time. But once you can reconstruct those ratios in the time domain, then you can take once you know and figure out the starting value, then you can go back through and then calculate an age. And so, because the carbon-14 will decay once it's out of communication with the atmosphere.
So what kind of research questions are you trying to answer right now?
Yeah, so I mean, the big one, so we have this event, the Paleoceanese thermomaximum. So this event's at 55.9 million years. And we know that the temperature, we've done, a lot, you'd say, well, how can you reconstruct the temperature back then? Well, one is, I gave you an example, for example, an organic compound, certain organic compounds will preferentially put they'll change their structure based on temperature. But we can also look at things, let's say the magnesium-calcium ratio of a microfossil. And that also depends on temperature. So if you know the composition of the ocean, the magnesium-calcium ratio, the amount of magnesium relative to calcium that's taken up by the shell is temperature dependent. Or we can look at, oxygen isotopes. So again, if we think about oxygen, there's an 18 oxygen and a 16 oxygen stable isotopes. And that process of taking the 16O and the 18O in the water and putting it into a calcium carbonated shell, that's temperature dependent. So we, again, fractionate the isotopes, but in this case, by not through photosynthesis with carbon, but essentially the uptake directly from the precipitation of a shell calcium carbonate from the water. And again, that shifts the isotopes, and that process is temperature dependent. And then what we can do is take all these different methods, and there's several other ones. And then we can, once, we say, they all give us the answer of 6 degrees, at the same location. Well, then you're pretty confident you've got 3 independent ways, completely unrelated independent ways to instruct the temperature. And then we can do that and you'd be very confident about how much the temperature actually changed. So each one of them on its own could have some caveats, or problems, what we call proxy problems. And but when we get 3 or 4 independent assessments that don't rely on each other, well, then we can get a fairly good understanding on something of temperature. So then the question is, once we realize we've got this time where the world goes crazy in terms of temperature, then we start asking questions like, okay, so what happens to the environment? One of the most fascinating ones that we figured out sort of about 20 years ago was that the hydrologic cycle changed. And so if you start warming the world, you start adding a lot of moisture into the atmosphere because warmer temperatures hold more water. But what ultimately happens is that water change, the seasonality of that, because as the water gets in the atmosphere, eventually it's got to come out as rain. And so once you get into a new mode, and what we quickly realized from the sediment, just looking at sediments, if we go across the PTM, it looks like just sort of massive flash floods, and we see on marine sequences suddenly these bursts of clay minerals that are coming from rivers, and they go right across the interval of warming. So you put it together and you're like, wow, it's like the hydrologic cycle and flooding is just completely changed in a warm world. You're in a whole new sort of hydrologic dynamic during these times.
Well, what do you mean? What do you see? What do you see the effects are of flooding typically?
So the most obvious one is, for example, there's some really nice ones for, your U.S. listeners. If you go off the New Jersey margin or, anywhere essentially centered on New Jersey, north and south, and you drill into these sequences and you hit the PTM. So before the PTM, your sedimentation is sort of coming along, and it's a mix of marine carbonates and some clays from rivers. And then you hit this weird interval, and suddenly, you've got very slow deposition, and suddenly you've got 20 meters of clay just pours out right at the start of this event. And the whole geology completely changes, but just exactly during this event. And so, the only way to get that out, and it's all terrestrial, so it's coming off the continent. And so once you figure that out, and then you go around the world, and there's great examples in Spain, New Zealand, pretty much any continental margin that we look at, there's this massive clay layer that's formed, but just during this very, very short event. And really the only way to get that is somehow you've got to get, and unfortunately there's very good examples like, a week ago in Valencia, or, last year in Libya and other places. And so what happens is when you get a lot of rain very, very, very quickly, especially in a dry area, what happens is you just strip all the mud, and so these rivers are coming out, but they're not clear. It's not clear water coming out. It's like, it looks like, big brown soup as these rivers are coming out. And of course it goes into the ocean. So
if I agree with you, I could say my sentiments exactly. It's just a joke you can use, bad joke.
And now I get it. That in itself is like one of the examples. There's a response that, interestingly, when you run, when people have run climate models, they say, okay, 100 years in the future, what's the world going to look like? And they come to this conclusion. And then what we go, so we look at the PTM, we say, yeah, we already sort of figured that out. But it's not only, the hydrologic cycle, all sorts of things. And so, for example, organisms, back in 2004, so going back, 20 years ago. We went and drilled pretty effectively the North Pole. We were at 88 point something degrees latitude, pretty close to the North Pole. And we drilled into the sediment. So you got to ship out there an icebreaker, 3 icebreakers. And we connect all the pipes, get down to the seafloor and start drilling. And we got down to this BTM horizon down about something like 350 meters below the seafloor. And we look at the interval, and again, it stands out. All the organic compounds suggest 6-degree warming. And, another odd thing is the sediments suddenly become laminated. And what does that mean? That means you've lost the oxygen, because in most places in the world, in the ocean, the sediments are what we call bioturbated. You have things like sea cucumbers, worms, other organisms going and constantly churning up the seafloor like wheat harvesters. But if you make the oxygen low enough, those organisms can't live there. And so the sediments, then you just get nice little layers in what we call laminated sediment. So the PTM goes laminated in the Arctic at that time, and in many other locations too. So again, and so you start thinking,
So what do you think conditions were like at this time? You said it was 6 degrees warmer approximately. So how long did it last, and what could you tell about life and about what was going on back then?
Yeah. And so the timing, it's really, really hard to get the onset. So we know it's less than 10,000 years, definitely, the onset. So this carbon burst and the warming all happens within 10,000 years, but it's probably faster. It's just that we don't have the ability to really get in there and nail the age of. So we know.
How thick is the layer?
Well, it depends where you are. So like on New Jersey, it's 20 meters thick, and that's just the onset, because you can imagine if you're in a shallow basin, let's say your water depth is 40 meters and you have, let's say, the wave base, and so the waves are constantly turning over. So if you suddenly pile up 20 meters, you can't pile up anymore. And so you can only fill up a hole so fast. And so we don't even see the whole event on the New Jersey margin. We just see the very start of it. But in our other place, if we're way out in the middle of the ocean, we do see the whole onset and the recovery. And that's the interesting thing. It's about, so you have the onset somewhere on the order of, let's just say, well, there's extreme people, some people have suggested really fast, almost instantaneous. I don't think there's good evidence for that, but I think it'd be safe.
You don't think there's good evidence for what?
That is extreme, instantaneous, sort of like within years. I think it's, if you really get into it and look at all the data, it's somewhere on the order of 5,000 years or so.
But how do you know? How could you tell that is based on thickness, or what do you think it is?
You can do some clever things. And so let's say you have at some location some asteroid. You can date the asteroids by radiometric too. So you get an absolute age. And then you can calculate the thickness of sediment between those ages, and you have, let's say, an average sedimentation. But then here's the problem is, of course, there is no average sedimentation rate across this event because everything changes. And so what you have to do is then do that same sort of exercise at multiple locations. And then you start constraining things like, okay, it can't be too much because then it wouldn't make sense at this site. It can't be, too long. And then so you start getting into these constraints where the onset's somewhere on the order of 5,000 years. And then the recovery is on the order of something 200,000, somewhere between 100 and 200,000, and which is a bit disturbing, when you think about it. So, I suppose on a really optimistic view, you could say, okay, we do whatever we want to the world over the next, 100 and 200 years. And we only have to wait another 200,000 years and get back to where it was. But that's not certainly in human lifetimes, that's not a good.
So what are you learning from studying this band? I mean, what are some of the other characteristics of what you found?
Yeah. So, gosh, yeah. I mean, I can just think of like, for us, what's probably been the most fascinating bit is you can go into, so there's a whole range of climate models that have been built by using, physics and chemistry, and modern processing. And there's a whole bunch of predictions. And so if there's a whole set of reports in this, what do they call the United Nations IPCC panel, the Intergovernmental Panel of Climate Change. I'll be honest, I've always, I've read all the documents. I understand the science extremely well, but there's a little bit of this sort of groupthink of like, okay, this is the way it must be because, and that leads to a bit of alarmist views. But you can step back and say, well, hey, here we have an event. Let's test these. So is the idea, for example, of an accelerated hydrologic cycle. So the IPCC documents suggest this, and we can go in and I can, emphatically say, yes, that's absolutely the case. You can say, things like, What happens at high latitudes? Do we lose sea ice? Absolutely. And so when we go up to the Arctic again across the PTM, there's no evidence for sea ice. And in fact, a really bizarre find there is you start finding, subtropical species living on the North Pole. And so very, very quickly you have organisms that are living down at, let's say, 20 degrees latitude, and suddenly they're free swimming up on the North Pole. I mean, it's extraordinary. But you can even go in and, for example, we did a bunch of work on the pollen there, because you start thinking, okay, if things get warm, you'd start thinking the vegetation might change. And sure enough, the pollen changes. You start seeing far more, for example, angiosperms, flowering plants instead of gymnosperm. And all of that shows up in the pollen, but just during this event. And so, yeah, the whole biology is you have the huge lateral, or let's say latitudinal migrations across this. Where the real interest, one big problem right now is if we go to low latitudes, there's a few sites and there's nothing there. And so we're actually losing all sorts of things across the BTM. It's almost, mind you, we only have one or two of these sites, but when we've looked at them, it becomes barren. It's just like the only thing living there is bacteria. And it may be the case that things are just too warm down on the equator for organisms to live. So that's something that what we need is really nice sites to really thoroughly test that. But the few sites that we do have so far, we just...
I don't know what you mean. You mean life was segmented in certain parts of the globe and it was just, you think, uninhabitable in other ones, or like...
Exactly. So, yeah, you can imagine that, let's say the waters at the equator are something 40 degrees centigrade or something. There's not a lot of life that's going to live at 40 degrees centigrade year round. Today's really warm oceans are about 30 degrees centigrade. So, and that's about the maximum you have with places in Asia, the Red Sea. So it doesn't, there's really nowhere in the modern ocean where you're above sort of 30 to C for any significant time. But then you start thinking about things like just how bodies function, and multicellular life has a really tough time at 40 degrees centigrade. So,
okay, so how do the fossils change? What do they look like in this layer, and then above this layer and below it? What do you notice?
Yeah, so like here's an example of a really cool bit. So you can go to a place in Wyoming if you get the chance, and you go to like the Bighorn Basin, it's sort of north central Wyoming. And there's this big bright red layer. And this has been known for a while, probably the settlers. It's very striking, and it goes for, tens of kilometers. And people had done early work, going back well before the 1990s, back in perhaps 100 years ago. And they'd done careful studies, and they realized that there was this bizarre chain in mammals across this vent. So as soon as you hit the red layer, suddenly you've got before the red layer, you have organisms such as these things called plesiodapids, which they don't exist anymore, but they sort of look like an otter, and a few other organisms. Then you hit this layer, and immediately above that, you have primates and things, what we call perissodactyls and artiodactyls. These are things like camels, rhinoceroses, and and so it looks like spontaneous evolution. And so people had noticed this, and they thought, maybe just a whole bunch of time missing there. And then we've gone through and, as a community, and gone to sites and realized, no, that time's continuous. So then you get this crazy idea like, okay, so what's going on? Is at the start of this event, things start getting so warm that organisms, including mammals, start migrating really far distances and get all the way up into high latitudes, 70, 80 degrees latitude. And then they can, if you have a land bridge up there, which existed at the time, then they can switch. So you can have an organism, let's say, that's living down originally, let's say, in low latitudes in Asia. You have this very rapid warming and starts migrating north, and then hits the land bridge. And of course, at high latitudes, the distances between continents gets very small because, at 80 degrees, as you do around a sphere, the distances aren't nearly as great as if you're trying to do that at the equator. And so now you got these organisms that were originally sort of, subtropical. Now they're living up at high latitudes, and then the event starts cooling down, but at the time they've already connected, and then they've migrated. And so you're suddenly in North America. Before the event, you've got one set of organisms. The event happens, and then bam, suddenly organisms are coming from halfway around the world and just suddenly in taking over. And it's very, very quick. It's not only things like mammals, but also plants, all sorts of organisms. So we see that absolutely in the marine environment. We see it in terrestrial environment.
Well, they should have been a great mixing then of the existing life on the planet, and then a resorting, right?
Yeah, that's exactly what we see. And so if you think of it, for us, it's sort of interesting is that we can't find any primate fossils until this event. And then bam, suddenly primates are on multiple continents. So there must have been some proto-primate, presumably it's slowly evolving somewhere. And then it was panacea, and then took over the planet. But we find this similar things in, for example, marine life. There's a type of marine life, single-celled organism, dinoflagellate. And we find that during this event, there's one subtropical genus, a thing called a pecadinium, just takes over the world. And so you go from, there may be 1% of this organism at, say, 30 degrees latitude and zero at anything north of that or south. And then suddenly during this event, you've got populations, 80, 90% of this one genus, all the way from 60 degrees north to 60 degrees south. And so it's like one genus.
Is that after this happened and creatures returned to the middle latitudes, or?
Yeah. And so like plants are a good one. And so plants, what happens is before the PTM, you have one set of plants. For example, if you go to Wyoming, during this event, you have plants just didn't exist anywhere around it. It's sort of like, where did they come from? And then after the events and things cool down, so sort of this 200,000 year decay afterwards, the plants come back sort of what they were before, but you've already changed things. And so the ecosystem's not exactly the same, not the exact same, genera and species, but similar one. And so you have what we call excursion time. And so during this event, things are just very, very oddly different in life. But then you get things that sort of come back the same, but they're not the same because, if an organism goes extinct, it doesn't reappear. And so some things migrated into refugia.
How do you know that, so when you do drilling, I would think you would get microfossils, fine. But how do you get the macro ones so you know that primates suddenly appeared? Are you able to correlate with land-based sampling and you just know the age because of the radioactive isotopes that you're using to date everything? Or how do you know it's at the same time?
So that is an absolutely fantastic question, and it's actually solved through these carbon isotopes that I mentioned earlier. And so what happens, of course, if you're out there in the middle of, let's say, the Pacific Ocean and you're drilling a site, and we get to this layer, the PTM, and we go to Wyoming, it's on land, so it's exposed in outcrops. So you drive your car and see it on a cliff. And then you say, well, how do you know that these two things are the same? Well, because what we can do is measure the carbon isotopes going across the event. And so we go into the ocean, we can look at, let's say, shells that are made out of calcium carbonate. And suddenly we hit this event and we have this whopping change in the ratio of 13 carbon to 12 carbon. So it gets very, very enriched in 12 carbon.
I thought beyond 40,000 years, though, you said carbon dating doesn't really help.
So that's for 14 carbon. So we have these three different isotopes. So 14 carbon decays very quickly, geologically quickly. And so after about 40,000 years, there's no carbon 14, but you still have the relative ratio of carbon 12 and 13. And so what's happening is some massive amount of presumably fossil fuel carbon is going into the system very quickly. And that changes the atmosphere. And because the carbon in the atmosphere is linked to the carbon in the ocean, the entire global carbon cycle gets flooded with 12 carbon. And so you can just generate records and then you can just line them up and you see this spike. And you can see the spike that goes right where the starts of the primates are on land, right where you get the excursion taxa in the ocean. You can find it in any carbon-bearing phase. So you can find it in organic molecules, carbonate. And so on the land, they've done it in things like gar teeth or soil nodules or, organic leaf compounds. So things like alkanes that are formed by, so these are long, they're hard to remove these alkanes because the bonds are hard to break. So they last for a long, long time. So you can just measure, you can take an alkane, pick, let's say an alkane with 25 carbon atoms and go through that. And suddenly you're measuring the same compound. But right as you hit this event, suddenly there's this whopping change in the isotopic composition of the alkanes. And, so any carbon phase that's linked into essentially Earth's carbon cycle changes dramatically. And it's not like anything else in the last 90 million years. It stands out.
Yeah, it sounds like a catastrophic event, I guess, happened, right?
A true catastrophic event is, for example, at the Cretaceous Paleogene boundary. This thing from the asteroid belt comes in, lands in the Yucatan Peninsula, at 24,000 kilometers an hour, and and we just get whacked, and that's the end of the dinosaurs and everything, or the Canadian dinosaurs.
But what would create such a massive spike in soil over such a short period of time?
Exactly. And so, and here comes the really fundamental question, and I can pose it to anyone who's listening here. The natural thought for most people is that, here's an example of exactly, not exactly, but somewhat similar to what we're doing as humans. A huge amount of carbon came into the system and drove climate change and drove all these other things like, changes in pH, changes in dissolved oxygen, the latitudinal distribution of animals and plants, sea ice, all of these things, a hydrologic cycle. And so everyone, I'd say most people in the community have jumped on it. I think that's actually wrong. And so what I think is going on is you're in a coupled system. What happens is, for other reasons, we start getting warming and we pass a tipping point. So we already know for about 4 million years, we've got slow warming going on Earth. And then this event happens, and it's after sort of a long-term warming. And so the other sort of end member possibility is, no, it's not that the carbon's driving the warming. It's that the warming starts driving carbon, which then that means that's a totally different way to view the world, because then what we have is, let's say we start warming the world, we start releasing carbon from other sources, that, you're moving things out of the steady state. And the most obvious way to do this is through methane. And so you start warming up the world, and things like, permafrost starts melting, or methane in the seafloor. And then as you start adding methane, that just, you're into a positive feedback, and then the whole world just sort of goes.
Well, is there a methane signature, or you can't? So
you can't, because methane has a very short time. So, it's a really powerful greenhouse gas, but, within sort of 10 years or so, methane converts to CO2. And so what we see in the geologic record during this event is absolutely a whole bunch of CO2 comes. But if you go and do some basic math equations, you realize if it was just CO2 coming in and you pick something like a volcano, the amount of CO2 doesn't even make sense. It's way too large. But methane, because the methane's produced through methanogenesis, again, you fractionate the isotopes. So methane has, on Earth's surface, for any significant size reservoir, methane's really, really enriched in 12 carbon. So just a little bit of methane gives you a giant signature in an isotope change. And then all the math makes sense.
what about solar activity? What if I don't know, there was a huge jump in solar activity for a period of time, or massive solar flares? Could that have done this? Temporarily warm the Earth a lot more than it had been?
I suppose in some sort of, you could always argue somehow the sun, suddenly, because the Earth's surface temperature depends on, three basic concepts of, essentially the amount of energy coming from the sun, our albedo, and, the amount that's reflected back, and then our greenhouse gases. So that combination, I don't think anyone's seriously suggested that suddenly we had a change in the flux of.
But why is that more improbable than a sudden change in Earth that can't be explained?
Yeah, I mean that's a good question. Well, the first thing is the sun itself wouldn't change the carbon isotope. So no matter what you have to do.
But what if it was again a sudden heating from solar activity that all of a sudden bursts on the scene for some reason?
Yeah, and then releases carbon somewhere on Earth. I mean,
well, it heats up. The sun hits us. We also radiate it out. There's no massive accumulation. Otherwise, the Earth would, I would guess it's a steady state. So if all of a sudden there's a lot more solar activity and the Earth can only get rid of, a certain amount of that energy, maybe then heat would build up for a period of time.
Yeah. So, I mean, again, there's sort of two different problems here, and they're somehow coupled. So we have the evidence for warming, and we have the evidence for carbon input. So, whatever the cause for warming it, okay, somehow that has to be linked to the input of carbon. So if you had some, in theory, if you suddenly, had a difference in solar input and it raised the temperature, it doesn't explain the carbon input. So again, you'd have to have a feedback. So releasing carbon.
Right. Well, like what could cause that? Again, if like, incredibly big volcanoes erupted, you would think the Earth would cool. How could you get such a huge sudden amount of carbon? if everything living on Earth died all of a sudden, and like in the same day, would that even be close enough to release, enough carbon to cause this? Like, where could it possibly have come from? Was there great tectonic action and huge methane deposits burped out? Could that be like, there's got to be some source of this, right?
Absolutely. And so you have one camp that has argued for sort of bizarre volcanism. And so somehow taking a bunch of normal volcanism doesn't have a significant difference. It's a very small difference in the ratio of carbon-12 to carbon-13. So in order to change, you can think of this as like, okay, suppose you have it's a bit wacko to think about, but suppose you have a swimming pool and a hot tub, right? And the swimming pool is white and the hot tub is some other color. You have to add something from the little hot tub into the pool to make it red. You can't take something pink, So it's a little bit different and suddenly turn it red. So what you got to figure out is that it's a basic math problem of mass balance. And so because normal volcanism doesn't have a composition radically different than the ocean atmosphere, the normal ocean atmosphere, you either have to come up with some absurd amount of volcanism, which even then, you get to values that are like just not fathomable, or you have to come up with some creative way, like the volcanism comes up, heats oil deposits, and then releases it. And so people have argued this, and even then the masses are huge. The way to get around the math problem is you have methane. And then so what we do know is that we don't know how much there is, but we know even today's world, there's lots of methane that is stored in both permafrost and in seafloor sediment. Huge amount. The question is, can you warm the planet up and then suddenly start discharging? So it's not like that methane is suddenly formed and then goes. The methane had been forming for millions of years, but you have a mechanism to suddenly get it out of the system. And if that's the case, then our own future becomes interesting, because that's not really even anywhere in the sort of IPCC reports,
I had thought that, one of the ways in which we could have sudden catastrophic climate change is that gigantic methane hydrates that are buried in the sea. Somehow there's a large earthquake which breaks them apart and they come to the surface and release massive amounts of methane. I don't know how possible it is, but, perhaps that's the way.
Yeah, it wouldn't be so much earthquakes, but you can just imagine if you have temperature. And so, it all depends on how much methane there's. So certainly people have suggested.
It just seems like no one has identified how possibly you could have this massive increase in carbon. Who has put numbers on this? How much of a dump of carbon, how many gigatons or teratons or whatever would be required to cause this over a period of time?
Well, I'm sort of laughing because, that was my Ph.D. thesis.
Oh, wow.
Yes, I have done all this.
You remember everything you ever wrote in it? Tell me about it. It's already 30 years ago.
Yeah, and so I got to think about that. Yeah, it's about 30 years ago. 28 years ago, I guess.
I remember like it was yesterday. Yeah.
Yeah.
So I know it'll take some time to remember, but
yeah, and I, did the crude modeling and all of that. So yes, but I hesitate because I hate promoting my, my own idea. This is the right way. But so far, and I'd still say,
I want your speculation and I welcome it. I'm not here to say like, oh, I have my own theory and I don't hear you say anything, there's no, that's not like I'm going to lose my professorship at my university or something. So you can speculate in it. I won't be upset at all.
And so, and so to do this, I still think like 30 years later, it's the best explanation. So if you warm the bottom waters by, let's say 5-6 degrees, of which there's plenty of evidence for that. And then all you have to do is you have to propagate heat down the geotherm. So today, the seafloor has some temperature. And then as you go below, as you start going down, the sediment gets warmer and warmer. At the same time, you've also got pressure. And so the combination gives you a lens or an area where you can precipitate methane. And that lens is huge. And so what happens is, how much methane exists in that lens, both as dissolved gas, as free gas, and as solid gas, what you talked about is gas hydrates or clathrates of methane. And the problem is those volumes or those masses, if you will, aren't very well constrained, even 30 years from, when we first started ingesting this. And you've had, in fact, it's worse because you've had people come along and really try to push other ideas without really understanding the basics for how methane's distributed. So there's a wide range in estimates right now. And then of course that's for today. And so then the problem comes is, okay, we go back, 56 million years. How much methane do we have then? And a similar argument also would apply to permafrost too, which also has a large amount of methane.
What would be a leading or a lagging event though? There has to be, I mean, I can understand, yes, you could figure out the lagging events. The permafrost will be affected once temperature goes up, but what again would cause this huge input of carbon? And again, like, I don't know if you remember from what you calculated, but was it teratons? I didn't even know the words for it.
The modern sort of carbon system today, if we think of the earth, the ocean, and that's somewhere on the order of about 35,000 gigatons or petagrams. So we'll just keep with gigatons. So 35,000 plus or minus for the ocean. And that's pretty easy to calculate today. The soil and humus and biomass today, it's on the order of, 2,500 gigatons. And then the atmosphere before we came along as humans had about, 600 or so. So the whole mass is, to make things really simple, is about 40,000 gigatons, okay, is the mass of carbon in the modern carbon cycle. And this mass is going back and forth between the atmosphere and the ocean by gas exchange. It's going back and forth between the terrestrial biomass and the atmosphere through photosynthesis and respiration. So this 40,000 gigatons is sort of sitting there. And each pool has a slightly different ratio of 12 carbon and 13 carbon, with the biomass being very enriched in 12 carbon because of the photosynthesis. And then there's sort of normal inputs and outputs. Before we came along as humans, it's on the order of about 0.4 gigatons per year. And then we're coming along now and we're adding about well, it's probably a little bit more than that now, about 10 gigatons of carbon per year. And so, over the last, and that's been sort of exponential.
So we're adding like 10 out of 40,000 total floating around.
Yeah. And then in total so far, we've added, it's on the order of, 200 gigatons so far.
Yeah, but what we're adding though is coming from a source. So that would be depleted. I mean, we're not really creating out of nothing, but well, most of it's not created.
Yeah. And so most of that's coming from, oil, coal, natural gas, which don't really participate in this sort of what we call the exogenic carbon cycle, where we have carbon spinning around on Earth's surface.
I guess so. I get exchangeable or free carbon. What would be the number on that? And then what does our current contribution represent as a percentage?
You have about 40,000 in the Earth, ocean, atmospheres. You have about 0.4 in and out of that system to places like oil, gas. And so, it takes millions of years to build up, oil and gas reservoirs. And, you have to bury the carbon and it's got to go through a bunch of processes. So you have this trickle in and trickle out from this rapidly spinning over carbon cycle. And then what we're doing as humans, we're tapping that big reservoir down below with, if you take all of the oil and natural gas, coal together, in sort of a significant pools of carbon, we're not talking like old dispersed carbon, just the conventional ones, you're talking somewhere on the order of 5,000 or 6,000 gigatons.
It was like, if I was God and I had a gigantic canister of carbon and I opened it, my goal is to warm the Earth right now about 6 degrees. How much carbon would I need to put out to do that?
Well, you don't have to be God because we're doing it right now.
Yeah, but you know what I mean? Like, what would be the calculation in order to emulate what you see in this boundary from 56 million years ago? What is the calculation of how much you estimate would need to be put out suddenly?
So that in itself is an interesting question. So there's two ways to get at the question you're asking. One is to ask, okay, if we have a carbon source, how much do we have to add to change the isotope? So forget about any temperature effect. And the amount, let's say if you want to do with methane, you have to add somewhere about 2,000 to 2,500 gigatons of carbon. So on order about what we will do over, the course of 300 or 400 years as humans. So, but back in that time, maybe over 5,000 years. And so that's about the mass that you're thinking if it's methane. If you want to say that it's some other source like volcano, then you get these numbers, like 50,000 gigatons, which is like 10 times more than we could possibly put in as humans from oil, gas, and coal. And so you start getting these bizarre numbers. But then you could turn it around and say, okay, how much do we have to add to cause the warming? So suppose it was a carbon drove all of the warming. That becomes in itself a really fascinating question because people have assumed for a while that we have something, fixed, what we call Earth sensitivity. And it's always been this idea that, okay, if we double the CO2 in the atmosphere, we increase the temperature by 3 degrees, sort of, we double the CO2. So then the question you say, so what we have to do is double the amount we can calculate the amount to cause a 6-degree warming across this event. The problem, though, is that we don't really know Earth's sensitivity that well. And in fact, until a couple of years ago, we had this very sort of standard view of Earth sensitivity. And absolutely everything these days coming out from all sorts of modeling and the geologic record suggests that the sensitivity is far worse than we thought. So for each bit of CO2 you add, the amount of temperature change you'd get is great, about twice as much as we originally thought about. So
you're saying it's more sensitive than thought.
Yeah, exactly. And so then you get to this really awkward thing is like, then the mass all starts getting to make sense. So if we add about 2,500 gigatons of carbon, if some of that warming is caused by some other mechanism, of which I can give you a good example, then it starts getting to this idea that, methane still nicely fits. So people had argued that couldn't be methane because if it's 2,500 gigatons, we couldn't get enough warming. But the problem is they were using sensitivity that we don't think is correct. And so there's these very strange arguments so you're hitting at some great questions.
If it is methane, then that makes the most sense. Where would a source of that much methane come from? How much methane would be needed, and what form do you imagine it would take? Could it come exogenously or endogenously only, or
You'd have to add about 2,500 gigatons of methane. And so what you can do is then
could a comet have a payload anywhere close to that large, or is that no way?
Well, people have argued that. So people have suggested a comet came in that leaves no trace except for the methane it all entered. But of course, that's not consistent with the fact that this event clearly has a geologic time to it. And so it's not like an instantaneous input of carbon. There's various ways to figure that out quickly. So if you just suddenly had, let's say, a comet add a whole bunch of carbon, what would happen is you flood the atmosphere, with that anomalous carbon, but the deep ocean wouldn't see it until you propagate that carbon to the deep ocean. So the analogy today is we're adding all this fossil fuel carbon to the atmosphere. We're starting to see it in the shallow ocean, but if we go to the deep Pacific and you collected water there, you have no idea that humans were even on Earth. And so
there's even more factors. Yeah. What's the disbursement rate, carbon inputs throughout the whole globe? And I guess, if you look at places where the disbursement would have been last or taking the longest, that'll give you a better idea of how long it was in effect for this elevated carbon, because it would have at least had to have been around to propagate to like the deep ocean and stuff.
Tried some very clever ways to do this. So for example, we can go to a deep ocean site, right? And we can collect organisms that lived on the bottom of the ocean. And we can collect organisms that were living in the surface that have now, they died and then sank. And that sinking time is, relatively fast on a geologic time scale. And then so you'd have two records from the exact same location, one from the deep ocean and one from the surface. And so if that carbon came in and hit the surface, you'd expect there to be a lag between those. And so that the surface organism would start changing first, and then there'd be a lag on the order of whatever turnover time the ocean is. So,
But unless what if the event happened in the deep ocean? Again, the methane, could there have been a massive methane deposit? Maybe there was, again, a big earthquake opens up a rift, releases a massive methane deposit, and the source is from the deep ocean.
So then you'd expect the other lag. And so the other way around, you'd see the deep ocean see it first.
And so it could bubble up very quickly. Like what is the time? So if on the surface I burp out a gigantic amount of methane, let's say, or farted out, versus like at the bottom of the ocean I do that, how long would it take to go in one direction versus the other? Is there any way to calculate that?
Yeah. And so like today, again, you got this problem because, so we know that time today, and it's on the order, it depends where you are in the ocean, because, the North Atlantic, there's an overall flow direction from the Atlantic Pacific. So in the deep Pacific, the waters last saw the atmosphere in about 1,600 years ago. Whereas in, let's say the deep Atlantic, it's on the order of, 800 years. And so
it's like 1,200 years on average, let's say.
Exactly. So it's somewhere around, 1,000 to 1,200 years on average today. So that if you perturb the atmosphere, it would take that long to see the record. Essentially the bottom of the Pacific seeing the Middle Ages
Well, all right, but so that's from the surface down. How about from below to the surface? I would think methane could bubble up on the order of days, circulate through, right?
Yeah, so if you could have methane actually bubble all the way up, but it turns out it's not so easy to get a bubble going all the way from very deep through the ocean and up into the surface layer and then ultimately the atmosphere. There's some
Right. It's like what size of a methane hydrate cluster would have to go into gaseous form in order to provide enough methane to warm the Earth 6 degrees, in a short period of time? Like what does that calculation look like? And are there deposits that are that large that are there today, or is it far larger?
So there's no single deposit that's anything like that. And so what it would have to be if it was methane hydrates or if it was permafrost or some combination of both, you'd have to have multiple places, all sort of releasing methane, across, wide swaths of Earth. So for example, if we go into somewhere like the Blake Ridge, which is off the coast of South Carolina, and so back when I was a graduate student, I was fortunate enough to go on one of these drilling ships where we went and tried to, quantify the amount of methane in that one deposit and the combination of free gas and methane hydrate. So the methane hydrate sits above free gas. You have bubbles down in this pore space of the sediment. And so we did some very clever ways to quantify that. And that deposit probably has on the order of, 30 gigatons. And so that's one of the larger ones. But we know that there's hundreds of these deposits. So again, we don't know the total amount, but some people say it can't be more than 1,000. But then you actually look at the way they figured out these calculations, like this doesn't make sense because in fact, they go to somewhere like the Blake Ridge and they say it's 0. And I'm like, well, no, I've actually been out there. It's about 30. And so, yeah. And so you get these strange things. We don't know the current mass that well. But certainly, I still think, 5,000 gigatons of methane in deep ocean today that's a reasonable value for present day. And so you can imagine if you'd take half the methane in today's ocean that's stored in the sediment, and it's been accumulating over millions of years into some steady state, you'd release it. And it turns out if you do the calculation, you say, okay, if we're going to warm the bottom water by 4 degrees in today's world, and you do it over a significant amount of time on the order of, let's say, several thousand years, you lose about half.
Why would it warm the bottom water when the sunlight doesn't even get there?
So that gets into the way you actually do this. If you think of the idea of threshold conditions, and some people, they've now come up with this. So we were talking about threshold conditions, 30 years ago, and now suddenly people are all on to this idea of a tipping point. But it's essentially the same phenomena. So the way I've always thought about this is today, for example, you have water sinking at high latitude, so around Antarctica in particular. And you ask, so the deep oceans are being filled by waters where they sink. And you say, well, okay, so the waters are, today, they start out at something, like, 0 degrees, and then they sink and then flow. And so the deep oceans, particularly the Pacific, yeah, they have a value of sort of, 0 to -1 degree C. And that's because their source, that's where they came from. But that source is fascinating because it depends heavily on sea ice. And so what happens is you take the water, you freeze the water, and when you do that, you exclude dissolved ions. The water becomes dense and sinks. So then you come to this funny idea. You say, wait a sec, okay, suppose you have a world and you're at high latitudes and you go from -3 degrees to -2 degrees. You still have sea ice, but as soon as you go from -2 to -1 degree, you can't form sea ice. So that whole process, you can have a very, very slow change in temperature, but you magically pass the phase boundary and you've now just changed a whole fundamental process on Earth's history, the way Earth works. And so that's what we call you can think of it at a really simple level. You have a rubber band. You start pulling the rubber band slowly, and eventually breaks, but it's not like you pulled it extra hard when it broke. You pass that point, you passed a tipping point where that suddenly the world changes. So if you have something like that, such as sea ice of again, that's now been modeled, it's really sort of interesting, so that you can suddenly change the deep ocean temperature by slowly changing temperature, let's say over millions of years. You can very, very quickly, once you hit that sea ice threshold, flip the ocean temperature in the deep ocean, on your, 1,000 years or so. So there's your mechanism to suddenly, now you go from a world where the bottom water is relatively cold to, suddenly warming it. And that has to affect, things like methane that are dependent highly on the temperature of bottom water.
What about when doing the sampling either on land? It would probably be a lot harder in water, but what if you're looking for microstrata, meaning you're thin slicing the drilling you're doing somehow, again, you're just doing incredibly thin slicing of layers. You want to see like almost exactly where this layer begins and what that transition zone looks like. What if you're able to identify the transition zone down to like a millimeter's thickness of a layer or even less? What would you see that you might overlook if you just brute force drill through a layer or, break off a layer?
So in most parts of the world, including during, the PETM or most of the geologic record, we have bioturbation. And so what happens is you can micro sample it. But what's happening is organisms are going along the seafloor and they're constantly churning it. So it'd be, a really crude analogy. It'd be like going to your lawn and you say, oh, I put the fertilizer, right at this point or whatever you want. And then you go through with a rototiller and then try to, and say, oh, now I'm going to well, it doesn't make any sense because you've now completely churned everything over. So you can't get anything on the timeline. And so in most places in the world, it's very, very difficult to get anything better than 1,000 solution because just the churning over of material. Where you have that ability, it's in laminated sediment, so that you've lost the bioturbation.
Right.
And so what we really want to do is get laminated sediment that goes through the start and, before, during, and after this. It turns out we find laminated sediment during the PTM, but it's already started. And in fact, the laminations are probably because we've warmed up the water. And as you warm up the water, you change the density. You also change the solubility of gas. And so at a location, suddenly your oxygen concentration is less, especially also if you include methane.
What if the place you're sampling was wet and that's why there was no lamination? And then once it dried, it suddenly dried and then things just froze in place. And that's why you have the lamination. So to do that's something like that.
Yeah, the places I'm talking about, we're like deep down in the ocean. So.
Oh, so you're seeing lamination down there too?
Yeah. And so like in the Arctic. And so, so right at the PTM, the sediments become laminated. And that's not the only place. It is several other places.
So what does it look like if you very carefully go through this layer, you look at what leads into it, you look at how it comes out of it. If you look as carefully as you can through as much laminated substrate as you can, what does it look like if you really examine it carefully, closely, understanding this perturbation?
We've been thinking of trying to do that for like 20 years. The problem is getting the right sediment and the right material. And so one of the problems, of course, is when the sediment goes laminated, right, you've lost the oxygen. And then things like the organisms on the benthic, the benthic organisms, the one you want to be recording the signal, they're not there because they can't live then. So then you got this odd problem. So you get this great record heading towards the event, and then your benthic record's gone. And so it's like, just when you want the benthic record to be recorded in laminated sediment, you don't have it anymore because it's laminated.
What would be the limiting feature that only could happen in a short period of time? The disappearance of, like you said, benthic organisms. That probably wouldn't be 1,000 years. That would probably be a narrower window is my guess. So what happenstance would have the narrowest window where therefore you could further narrow what's going on, at least in a part of these samples?
So I think the way to get around this, and we may have the records now, although this is a little bit of an aside. And if you have any listeners that are really followed about the PTM, they're going to find this sort of interesting controversy. So imagine if you have a hole, okay, like a big hole on the seafloor, and you're near a continental margin. I've already shared with you that the hydrologic cycle goes nuts. And so, for example, on the New Jersey margin, you're piling up sediment, I don't know the exact rate off the top of my head, several centimeters per 1,000 years, so millimeters per year, less than millimeter a year. And then suddenly hit this event and you've got 20 meters of sediment piled up very, very quickly. But you don't have a hole really because the sediment's just what we call prograding. It's moving outwards across the margin very fast. But suppose you have a hole there and you get the sediment and the hole's deep enough. In theory, now instead of getting around the problem of trying to get a laminated sediment, what happens is your sedimentation rate goes through the roof. And so now you'd suddenly be, even if you had bioturbation, you could get a very good time series. So suppose it's now 100 meters thick across but your bioturbation is only 10 centimeters, then you should be able to start disentangling things. So what they have found is if you go to places in the North Sea, you find craters, for example, that are filled with PETM sediment. What people have done is they've, in my opinion, incorrectly, they've assumed that those craters are then the source of during the PTM. And I don't think that's the right answer. I think what it is you had craters there and they got filled very fast, or PTM. And so in those sediments, we may actually have the sort of records that we might be able to tease some of this information out. We just have to somehow as a community first figure out whether the sediment itself has anything to do with the PTM, or is it material that has been moved by processes that have happened because the environment changed so quickly. So, but all of that, I mean, we're talking, those sort of arguments are happening right now at 2023, 2024. So
right now, what is the most reliable and shortest duration of time that you could say, yes, we're looking at 1,000 years here, or maybe you can get it down to 100 years? What is the smallest?
Of rate, and of course the ones in the deep sea where you might get the best records, we also have the problem is the pH change, and so we start dissolving up the records, so the records get compressed. So the best records that we might be able to get right now, where we're really confident we're sort of getting the onset of the event, we're talking on the 1,000-year time scale, which if you asked, let's say, 30 years ago, whether you could start looking at events 55 million years ago on the 1,000-year time scale, you'd be like, there's no way you could even do that. But yeah, we can actually correlate because of the carbon isotope signals. We can take sites from all around the world and we can link them well within 1,000 years, but probably not much. We probably couldn't say, okay, these two locations, even at the same site, because of the bioturbation.
I don't think 1,000 years is like a geologist's fact map, huh?
Yeah, and so I think so far, I think that's what we're looking at. Now, again, we find sites.
So what do you see if you look at 1,000-year estimated window? Does that give you any more clarity, or is it still way too long to really?
At that level, it looks like it's almost instantaneous, and so that's why we know that it's on the order of something like 5,000 years or less. It's not truly. So there's clearly a step, and you can find samples, that are recording changes in between, but some of that's affected by bioturbation. So even if you had an instantaneous, event, and, and a good way to think about this is something like, again, the KPG boundary, where we, almost assuredly had an instantaneous event because this big rock hit us. But if you go into a deep sea signal and you look for something like iridium, it's stretched out over, several centimeters, or, tens of centimeters in cases, because it's been spun over afterwards. And so you can't, even though it's an instantaneous event, it doesn't look like that in the record. You've smeared it. So, yeah.
Okay. So where do you go from here? What's next in trying to tease this apart? It sounds like you've been working on this for 30 years at least, and you're not getting up.
Disappointing because, I've won awards and all sorts of things. In my own back of my mind, I'm like, geez, I'm 60 years old and I still haven't figured this out. So it's
a hard puzzle. Can't blame you,
Yeah, and so it's
shame on you that you haven't figured this out.
Yeah, and so I mean, I know the problem, better than almost anyone, but maybe better than anyone. But it really bugs me that I haven't figured out the answer. That even in my own head, I have not convinced myself that I'm even that really, really close to the answer yet. So where you can ask where are things going right now, and so
what if you drill out a large core and you pull it out like a big old plug, undisturbed, and then you put it in in lab conditions, maybe in a blanket of nitrogen, and you do like non-destructive testing on the interior of the core, so it's not exposed to air, let's say, or it would take a long time for it to migrate in. What could you see that you couldn't see just with brute force drilling or sampling that exposes a layer or a surface to the current ambient?
If you collect a core, right, and in some of these places we've got very clever ways, so we're not actually get into all sorts of ways about how to collect sediment cores, but in certain environments, and if we're lucky, you can think of it as like shooting a straw in, a big straw. And so we're not actually spinning the sediment from the drilling, but you still have the problem of that the sediment, has been bioturbated by organisms well before we go there. So we can do that. You can collect the cores, and routinely now what we do is we send it down various physical property tracks. And so these are instruments. You take the core and it's still sitting in its liner. So when you collect a core, the sediment itself is sitting in a plastic liner. And you can take that liner and you can put it down and measure things like, the density. You do that through like gamma ray attenuation, and that gives you a really accurate way of what the density is. Or you can do now the ability to do X-ray fluorescence. And so you can get the chemistry of the sediment through the liner before we even open up the core. And you can do that at, centimeter scale resolutions. We've got these amazing records now that go across the event. And clearly, that when you hit this PETM event, you see everything changes, and like the deep sea, as I mentioned, the pH changes. So you dissolve up the carbonate. So things like, the magnetic properties suddenly, increase because you've gotten rid of all the dilutants, carbonate, or, various chemistry, like the aluminum content goes up because, again, you've lost all the calcium carbonate. So yeah, we get those sort of records, but to try to figure out, which comes first, the warming or the carbon, we've not been able to disentangle that yet. And that's such a fundamental question and a very important one for society. So if the PETM, if the carbon is largely a response to warming, oh my gosh, we could be in a lot worse situation 100, 200 years. I mean, you and I will be dead, but our, prodigy would, sort of get hammered by some carbon output that, it's not really in models around, because a lot of people, they just literally, I've had discussions with people, on these IPCC documents and things, and they don't want to talk about things beyond 100 years because, well, your unknowns start getting large, and they don't want people in the sort of the average citizen that hasn't spent a lot of time thinking about this stuff. They don't want them to get confused by uncertainty. And so I understand it at one level, but at another level, it's a bit disappointing. And so we're constantly giving people information saying, oh, this might be what it's going to be like in 50 years or 100 years, rather than like, well, geez, maybe that's not the right way to think about things. You got to think like 500 years in the future, and things may be radically different than if we just think on the sort of 50 or 100-year time scale. So, yeah.
Well, very good. I've soothed these issues, but no, it was very interesting. Yeah. Where can people go to learn more and ask their own questions and, see some of your material and everything? What's the best place?
I mean, I've tried to fix up the Wikipedia pages on the PETM, but each time I do it, it's pretty funny. I actually got accused of cyberbullying one time because, somebody said I didn't write the correct things, and and you all know when
Wikipedia, it's not good. It's like a wasteland of intellect, it seems like.
Yeah, so it's pretty funny. And then, somebody came back and changed it. I'm like, oh, God, you really don't understand. And so, yeah, there was a nice paper. And unfortunately, I don't know if it's under paywall or not. It was in the annual reviews of Earth Science, but it's old in the sense it's 2011. But
geologically old.
Yeah, like community old. So, I mean, 12, 13 years ago is a really nice summary about the event by friend McInerney and Wing. But I'm not sure if that's, if just the average person can just go on and pick that up. There's a nice National Geographic article put out on it. Some, really, it's pretty decent article about that. So there is information in public. It's been tough trying to share people that, a lot of people, they can't, they want to talk about climate change and understand it. And here, we've been sitting on this for now 30 years and saying, if you really want to understand climate change, not only do you have to sort of project into the future, but you have to go into the past and look at the best example for what's happening right now. And you're forced to really say, whoa, some of these ideas that people have put forward are clearly qualitatively right. But where the quantitative bit gets problematic is things like feedbacks and, really obvious ones like how do clouds change during the PETM or in our future? And that radically changes how you model something like the temperature effect.
Increased respiration of plants up to a point with increased carbon dioxide.
Yeah. So there's all these feedbacks, but what we can say definitely is that all the major boxes, things like changes pH, change in the carbon cycle, temperature, biology, sea ice, dissolved oxygen. So all of these parameters that, people have suggested may happen, they clearly happen across CTM. And so, yeah.
Okay. Well, very good. Well, thanks for coming on the podcast and being so patient and being willing to speculate and all that stuff. I really appreciate you coming.
Thank you for listening to the Good Question Podcast. Please email support@thegoodquestionpodcast.com if you have any referrals to great guests for us to interview. Visit thegoodquestionpodcast.com to hear more interviews. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast.
By some carbon output that it's not really in models around, because a lot of people, they just literally, I've had discussions with people on these IPCC documents and things, and they don't want to talk about things beyond 100 years because, well, your unknowns start getting large, and they don't want people in the sort of the average citizen that hasn't spent a lot of time thinking about this stuff, they don't want them to get confused by uncertainty. And so I understand it at one level, but at another level, it's a bit disappointing. And so we're constantly giving people information saying, oh, this might be what it's going to be like in 50 years or 100 years, rather than like, well, geez, maybe that's not the right way to think about things. You got to think like 500 years in the future, and things may be radically different than if we just think on the sort of 50 or 100-year time scale. So, yeah.
Well, very good. I've soothed these issues, but no, it was very interesting. Yeah. Where can people go to learn more and ask their own questions and, see some of your material and everything? What's the best place?
I mean, I've tried to fix up the Wikipedia pages on the PTM, but each time I do it, it's pretty funny. I actually got accused of cyberbullying one time because, somebody said I didn't write the correct things, and I'm, and you all know when
Wikipedia, it's not good. It's like a wasteland of intellect, it seems like.
Yeah, so it's pretty funny. And then, somebody came back and changed it. I'm like, oh, God, you really don't understand. And so, yeah, there was a nice paper. Unfortunately, I don't know if it's under paywall or not. It was in the annual reviews of Earth Science, but it's old in the sense it's 2011. But
geologically old.
Yeah, like community old. So, 12, 13 years ago is a really nice summary about the event by friend McInerney and Wing. But I'm not sure if that's, if just the average person can just go on and pick that up. There was a nice National Geographic article, put out on it. Really, it was a pretty decent article about that. So there is information in public. It's been tough trying to share people that, a lot of people, they can't, they want to talk about climate change and understand it. And here, we've been sitting on this for now 30 years and saying, if you really want to understand climate change, not only you have to sort of project into the future, but you have to go into the past and look at the best example for what's happening right now. And you're forced to really say, whoa, some of these ideas that people have put forward are clearly qualitatively right. But where the quantitative bit gets problematic is things like feedbacks and, really obvious ones like how do clouds change during the PTM or in our future? And that radically changes how you model something like the temperature effect.
Yep. Increased respiration of plants up to a point with increased carbon dioxide.
Yeah. So there's all these feedbacks, but what we can say definitely is that all the major boxes, things like changes pH, change in the carbon cycle, temperature, biology, sea ice, dissolved oxygen. So all of these parameters that, people have suggested may happen, they clearly happen across CTM. And so, yeah.
Okay. Well, very good. Well, thanks for coming on the podcast and being so patient and being willing to speculate and all that stuff. I really appreciate you coming.
Thank you for listening to the Good Question Podcast. Please email support@thegoodquestionpodcast.com if you have any referrals to great guests for us to interview. Visit thegoodquestionpodcast.com to hear more interviews. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast.